Dear students, in this section we are going to learn the concept of equivalent focal length of lens combination. We know the lens formula, that is 1 upon V minus 1 upon U equal to 1 upon F. We know this formula is applicable for thin lenses. Thin lenses means we consider the thickness of lens as negligible, right? We consider very thin at the middle part. Now consider one situation. Suppose we have placed n lenses in contact with each other. In diagram you can observe the 3 lenses, but this is a combination of the n lenses, right? Now consider an object is placed at a distance u from the first lens. Because we have considered thin lens and thickness of this lens is negligible, that we can consider the thickness of this combination also negligible, right? That means the distance of this object from any of the lens can be considered as u. Now here consider one situation. Suppose we are interested to find the image position formed by this combination. One method is we first consider the first lens and find the image formed by the first lens, then image formed by the first lens will act as a object for the second lens, and again we use the same formula and we will find the image position from the second lens, and from the second lens image form will act as a object for the third lens, and so on. But this is a very lengthy process. Here we will use a simple formula, and here we are going to derive a simple formula which can be applied for combination of the lens. Suppose object distance here is u and image distance from the first lens, suppose it is v1. So we can use the lens formula for the first lens, that is 1 upon f1 equal to 1 upon v1 minus 1 upon u. This is for the first lens. Say this equation number 1, right? Now this v1 will act as an object for the second lens. Again we will use the lens formula. That means for the second lens we can write 1 upon f2 equal to 1 upon v2. Suppose v2 is the image distance from the second lens and object distance here is v1. So this formula is applicable. Say this equation number 2. And this can be done for the n lenses one by one. So let us write for nth lens, that is 1 upon fn equal to 1 upon v. V is the distance of the image formed by the final lens, right? And object distance for the last lens is say vn. So we can use this formula. This is say equation number 3. There may be n equations we have not written. So here we can do one thing, we can add the all equation, we can add the left hand side and right hand side part of the equation. We can observe here, if we add the equations, this and this will get cancelled. Similarly this will cancel with the this equation which we have not written, and this will also get cancelled. That means we will have this term, summation of these up to the n term, and we will have this term finally minus 1 upon u term. So here we can write, after adding all equation, that is 1 upon f1 plus 1 upon f2 up to the n term, and this is equal to 1 upon v minus 1 upon u. And we know the lens formula, we know this quantity is equal to 1 upon capital F. Capital F, here we can consider the equivalent focal length of the combination, and u is the object distance from the combination of the lens, and v is the image distance from the combination of the lens, right? Now we can write equivalent focal length as 1 upon f equal to 1 upon f1 plus 1 upon f2 plus 1 upon f3 up to n term. So let us write the final conclusion, that is, if n number of the lenses of focal length f1, f2, f3 up to n are joined together or placed together, then the equivalent focal length is given by the formula 1 upon f equal to 1 upon f1 plus 1 upon f2 plus 1 upon f3 up to n term. And for the sign convention, will use the same sign convention which we used in the length section. That means the focal length of converging lens is taken as positive and diverging lens is taken as negative. So here up to this point we learn the concept. Now we are going to apply the concept through certain selected illustrations. In this illustration, we are given an equiconvex lens of focal length capital F. This is the equiconvex lens of focal length capital F. This lens is cut symmetrically perpendicular to the principal axis. That means from middle like this, we have cut this lens and we got two parts of equal size, 1 and 2. Calculate focal length of the lens if both parts are arranged like case 1 and case 2. That means we need to calculate the equivalent focal length in case 1 and case 2, right? We know the lens maker formula. Lens maker formula relate focal length with the radius of curvature of the lens, right? So we can write lens maker formula as 1 upon f equal to mu minus 1 upon r1 minus 1 upon r2, right? Mu is the relative refractive index of material of the lens. That means mu equal to refractive index of material of the lens divided by refractive index of the medium. If lens is placed in air, we can write mu equal to refractive index of the medium divided by 1. That means mu equal to here the refractive index of material of the lens, right? Because we are considering lens is placed in air. First of all, let us find the focal length of uncut lens in term of its radius of curvature. Because it is equiconvex lens, that means magnitude wise r1 and r2 will be same, right? r1 is the radius of curvature of this surface, r2 is radius of curvature of this surface. We can consider here rays are falling on this lens from the left side. That means any distance in the leftward direction can be considered as negative, rightward direction from this point consider as a positive sign with positive sign, right? So let us find the focal length of the uncut lens. We can write f naught 1 upon f naught equal to mu minus 1 upon r minus 1 upon minus r. We have taken this surface radius of curvature with a positive sign, right? And r2, that is the radius of curvature of this surface, center of curvature will lie here. We will measure from here to here. That means we are moving in the leftward direction while calculating the value of r2. That's why we have put negative sign here, right? Now we can solve here. This will be equal to mu minus 1 and this is equal to 1 upon r plus 1 upon r. That is mu minus 1 2 divided by r, right? Now we can write f naught equal to capital R divided by 2 mu minus 1. Okay, this is the focal length of uncut lens. Now we have cut the lens like this. Okay, this is the first part, this is the second part. Let us calculate the focal length of the first and second part, right? So here we'll use the lens maker formula, this formula again. For this part we can consider this surface as a plane. This surface actually is it is a plane surface. The radius of curvature of the plane surface is infinite and radius of curvature of this is capital R and center of curvature will lie on the right hand side. That means we will measure from left to right. That means capital R for this surface is positive and for this surface is negative, and refractive index will be the same. So this focal length, let us call this f1. f1 equal to 1 upon f1 equal to mu minus 1 and 1 upon r minus 1 upon infinite. 1 upon infinite equal to 0. So 1 upon f1 equal to mu minus 1 divided by r, right? We can write here f1 equal to r divided by mu minus 1. If we compare this focal length with this focal length, we will find the focal length of this part is twice the focal length of the original part. So we can write f1 equal to 2f naught. Similarly, let us calculate the focal length of this part. we will again use the same lens maker formula. We can observe here the radius of curvature for the first surface. This will be the first surface for this part. This is infinite, and radius of curvature magnitude wise is capital R, but center of curvature will in the left hand side. That means we will measure from right to left. That means we should substitute the negative sign while writing the radius of curvature, right? That's why we have put here negative sign. Now we can write 1 upon f2 equal to mu minus 1 divided by capital R. So f2 is equal to r divided by mu minus 1. Now we can compare with the original focal length. This is twice the original focal length. We can observe here the focal length of the both part is same by the magnitude wise, also sign wise. So let us place the combinations, first and second combination. So let us first calculate the equivalent focal length of this combination. We will use the same formula, that is 1 upon f equal to 1 upon f1 plus 1 upon f2 and f1 upon fn if there are n combination, n lenses. But here in this case, its particular case, we have the two lenses. So here we can write 1 upon f equal to 1 upon f1. Let us call this combination focal length as f1. So 1 upon f1 equal to 1 upon 2 f naught plus 1 upon 2 f naught, because the focal length of this part and this part was 2 f naught. So we can write 1 upon f1 equal to 1 upon 2 f naught plus 1 upon 2 f naught. So this is equal to 1 upon f naught. That means f1 equal to f naught. Okay. Now let us calculate the equivalent focal length of this combination. Again we use the lens combination formula, and here we can write this focal length as 2 f naught. This is again 2 f naught. So 1 upon f2 equal to 1 upon 2 f naught plus 1 upon 2 f naught. That means we can write that is equal to 1 upon f naught. That means f2 equal to f naught, right? So here we can say focal length of the both combination will be same and equal to the focal length of the uncut lens. That means we can observe if we place lens like this or like this, the focal length of the combination will be the same as the previous or uncut lens. Okay.